That roof is on fire. We gonna take it high.
The distance of Q3 from Q1. Let's look into that. That distance. Oh, sorry about that. All right. So let's remember we are saying we are calculating the total electric field exerted by Q1 and Q2 onto Q3. So the distance of Q1 to Q3 is these 2 centimeters. So here our charge is supposed to be 1 nanocoulomb, but we wrote 2. Yeah, everywhere we wrote 2 instead of 1. Guys, why didn't you stop me? You were here. Yeah, I think that's the only error that I noticed while I was quiet and thinking. And from here we have this part, 3 by 10 to the negative 9 over 0.04. Yeah, I believe everything is okay now. So please plug in the values so that we can calculate the answer. Please be louder, please. Negative 8. Your answer is different from mine. Can I get someone's opinion, answer? Alright, there's also something that we need to be careful about that I forgot to mention. You have your force, you have your Q3 here, you have your Q1 here, and your Q2 here. The force of Q1 on 3, because these two are both positive, is going to move in this direction, this is going to be your F1 on 3. It is pushing it to the left. But because this one is negative, it is going to be attracted to it, right? So it's going to pull it towards itself. It is going to be pulled, it is also going to pull it towards it. So that's going to be F of F2 on 3. So let's check that our signs are okay here. We said in here we are just going to put them in vector form. So in vector form, we take positive S to the right. Now our force due to 1 nanocoulomb is this one, and it has to be to the left. Do you guys see that? Our force has to be to the left. The force due to 1 nanocoulomb has to be towards the left. So we are going to have to put a negative here and a positive here. That's the error that we almost did. Maybe that's why we have this value. From here, why did I put a negative here? The force of, this is the force of Q2 on Q3. So that's the one that goes to the right. So it's positive. May you redo it again? Times 10 to the -5. Yeah, so because it is in the x direction, we'll write I hat because it's in vector form. So this is how you do it using the superposition formula. Now, there's another way to do it. I think that one is better. It is not prone to errors like this one. And it is to say we are going to add two forces. The net force that we are going to calculate for is going to be the force of 1 on 3 plus the force of 2 on 3. So now you're going to find the force of 1 on 3, which is going to be 9 by 10 to the 9 multiplied by 1 by 10 to the -9, which is our Q1, multiplied by, I should have written the formula down. Now I'm forgetting stuff. So our formula, can you guys give us our formula? It's going to be K times Q1 and Q3 over R squared of 1 and 3, which is going to be 9 by 10 to the 9 multiplied by 1 by 10 to the -9 multiplied by 5 by 10 to the -9. Both of them are positive. So the distance between them is 0.02 squared. So what do we get?
Uh,
1.13 times 10 to the power -4. Guys, do you all agree? I said you need to also be doing this, calculating this quantity on your own, so that we can help each other to not make any mistakes. And guys, remember, you'll be using these videos again in your preparation for the final exams, the semester tests. So if you are not really helping us in finding correct values, yeah, your discussion is going to be prone to errors. You might discuss you might discuss with a video with too many errors. So help out in calculating. Be active. Is this the right value?
yes.
All right. So that was Q1 and Q3. Now we are going to deal with Q2 and Q3. So let's move. Now let's calculate F Q2 on 3. That's going to be K Q2 Q3 over R squared of 1 and 3. I mean 2 and 3. So we have 9 by 10 to the 9 multiplied by Q2 is, what's the value of Q2? 3 by 10 to the negative 9. Remember, even though it's negative, we are taking the magnitude. There's a magnitude here. 5 by 9 to the 9, 5 by 10 to the 9 over u 0.04, which is 4 centimeters. So what's our value here? Hello? Do you all agree?
Yes, sir.
All right. So because we were writing this as a vector and we are only working in the x direction, we'll put I hat here. I hat. Now let's find the net force. The net force will be F net is F1 on 3 plus F2 on 3. Alright, there's something that we said about vectors, right? If we are going to write this as a vector, we need to be careful of the direction, not just the magnitude. So we said now, looking at the direction of 1 on 3, it's to the left and the left is negative, but 2 on 3 is to the right. So we need to change our value a little bit and give it a negative now, so that we are able to say now the negative 1.13 by 10 to the negative 4 plus 8.44 by 10 to the negative 5. What's the magnitude? I mean, not the magnitude. What's the total?
It's negative 2.86 times 10 to the power negative 9.
2.86 times 10 to the power negative 5. Alright. I had. Thank you. So as you can see, I think this value is the same as this one, unless I forgot 2 negative 2.8 negative, yeah, they are the same. So if you understand this one better, you will use this one, but if you understand this one better, you will use this one. Both of them are very mindful of the direction because we are using vectors, so we need to be flawless. Are there any questions so far? Alright, the next question says, two equal positive charges Q1 and Q2 which have the same magnitude of 2 microcoulomb are located at x is 0, y is 0.3 and y is 0, okay, x is 0 and y is that respectively. So what are the magnitude and direction of the total electric force that Q1 and Q2 exert on the charge on the fed charge 4 microcoulomb at this position. It's a lot to take in. Let's read it again one by one. Before we read it again, I just want to check that there's no diagram. Some questions have diagrams, so I just want to check. Now what we are going to do is to throw whatever they said. So we know on the x-axis, somewhere on the x-axis, at x is 0, y is 0.3. So we also have the y-axis now. We also have the y-axis. So on the y-axis at y is 0.3, there is a charge Q1 here. And at x is equal to 0, y negative 3, there's another charge here, Q2. The respectively, remember the respectively says the first one takes the first, the second, the second. So this is at negative 0.3. What are the magnitude and direction of total electric field Q1 and Q2 exert? I mean electric force Q1 and Q2 exert on the fed charge, which is at 0.4 on the x, 0 on the y. So this is 0.4 on the x. We have Q here. All right. So Q1 and Q2 have the same magnitude, which is 2 microcoulomb, but Q, the big Q, has 4 microcoulombs. Do you guys have any idea on how we are going to deal with this? How are we going to approach this question? Hello? All right. First, we draw the formula. I mean, we write down the formula. K, Q1, Q2 over R squared. We have the charges. We know K. What is R? Most of the time, R is going to be what's confusing. So let's see. How is R defined? R is the distance between the two. So that means the distance between the two, the distance between these two this is our R. And because we are saying we want to find the force that Q1 exerts on BQ, we will call this Q3. So 1 on Q3 will be here. Let's see the charges. The magnitudes of the charges are both positive, meaning it is going to be repelled. So this force that you see here is Q1. This is force of Q1 on Q3. We say this will be Q3. It's pulling it down. It's pushing it down. But Q2 on Q3 is pushing it upwards. So this is force of Q2 on 3. So as you can see, the directions now can be broken into components if you want to add them. And if you are going to break something into components, you first have to define it in terms of its components. So our forces have to now be defined in terms of components. So in this formula, if you were to break it, if you were to write it in terms of components, you would put the arrow on the F and then show that there is a unit vector associated with it. Now let's find these forces one by one. I realize that when we combine them, it makes stuff complicated. Now we're going to say F2 on 3. is k q2 q3 over r squared of 2 and 3. What's our r hat? Our r hat is our unit vector. To find the unit vector r hat, you need to have the vector r over its magnitude, right? But what is r? R as a vector first. What is the vector that we can take out from here? Do you remember, guys, how do we find vectors? From this charge to this charge, how can you walk such that we have a vector? How can you walk to Q3 so that we have a vector? R is the distance vector in this case.
Aren't you going to use Pythagoras?
Yes, we can use Pythagoras to find the distance, but what about to find the vector so that it has components? Should we also use Pythagoras for that? We can. You'll find that there's a couple of ways to solve these problems. So for the first one, in fact, for this question, I'll use one method and I will vary methods as we move on. And we'll choose the one that you think it's simpler to use. So to find the vector from Q2 to Q3, you can walk to the origin and then walk to Q3 from the origin, right? These are the two vectors. And if you walk from here to here, the distance that you are walking is positive because you are moving upwards. So your vector would be sorry, in fact, you are going to say your vector is the positive 0.4 in the x. Okay, why am I getting confused when it gets here? Is it positive or negative? Vector-wise.
Isn't it negative?
Alright, since I forgot, I'm gonna have to do something, alright? Please excuse me, I'm a human being too. So I'm going to say this point is called 0 on the x, negative 0.3. This is 0.1, right? This is 0.1 and this is 0.2. So 0.2, we are going to call it 0.4 on the x, 0 on the y. And I want to find a vector, not a vector, but I want to find, yes, a vector from P1 to P2. This vector, I will call it R. And that vector, I can find it by subtracting 0.40, which is 0.2 from 0.1. This is how we find vectors. You take 2 points and you subtract them. You subtract the ending from the beginning. So if we subtract here, you'll say 0.4 minus 0, you get 0.4 I had. 0 minus negative 0.3, you get positive 0.3 j hat. So as you can see, your vector has to be positive, right? Your vector has to be positive. So this is going to be plus 0.3 j hat. This is the vector. After finding the vector, you find the magnitude, which is going to be 0.4 squared plus 0.3 squared. Please help us find this magnitude quick. Alright, 0.5. I want to write this here because if this is going to be your notes, they need to be clear, guys. They need to be clear. Here I just wrote on a part that's not going to be part of the notes. As you can see, I wrote out of the page. This is out of the page. So we said R and we found R to be 0.5 meters. Is it meters? Yes, meters. So we have R as the magnitude. We also have R as the vector. Let's find the unit vector. So the unit vector R hat is R as a vector over R as a magnitude, which is going to be 0.4 I hat plus 0.3 J hat all over a magnitude of 0.5. Okay, we can leave it as it is. And then let's go back. We said to find these forces. To find these forces, we are going to do what? We are going to take this formula, multiply the charges and divide by the distance, and then multiply by the unit vector. So let's do that. This is going to be F2 on 3, and F2 on 3 is Q2 Q3 over R squared of 1 of 2 and 3 R hat. So this is going to be 9 by 10 to the 9 multiplied by what? What is Q2? 2 microcoulombs. 2 by 10 to the negative 6, and the big Q is 4 by 10 to the negative 6. And then we divide everything by the distance. The distance is 0.5 squared. So the distance squared. And then our unit vector. Our unit vector says 0.4 over 0.5 I hat plus 0.3 over 0.5 J hat. Right? So our force F2 and 3 you first multiply the I hat direction with all this quantity and then multiply the J hat, or maybe multiply all this quantity alone and then just multiply by I hat, repeat it again with J hat. In any case, our value has to be in terms of I and J because now it's a vector in its components. You were about to give me an answer, I hope.
As I got 0.23 I had
0.23 I had
and 0.17 J had.
plus 0.17 J hat. All right. I'm gonna do it again on my side just to check too. Did someone also find the same answer before I do it? Yeah, I also found this. I'm satisfied with your answer. So yeah, this is just the force that Q2 exerts on Q3. We are expecting that force to be positive in both of its components because it's moving upwards. So the x is positive and the y is positive. So we are safe. Now let's calculate 1 and 3. 1 and 3. The force of 1 on 3. So we are going to do the same thing. Find the vector. After finding the vector, find the force. Find the unit vector and then find the force. So what is the vector that's from Q1 on to Q3? We will do the same thing because it was confusing that time. It was confusing to just guess. I no longer want to guess again. So we will call Q1 P1 and Q1 is at 0 point something. It is at it is at 0 0.30 and Q3 is at 0 0.40. No, this one is at 0 0.3, but this one is at 0 0.40. Right? 0 0.3. The big Q is at 0.2, which is 0 0.40. And now to find the unit vector, we will call it P1, P2 is gonna be 0.2 minus 0.1, 0 0.4 minus 0 0.3. So that's gonna be 0 0.4, which is 0 0.4 minus 0, which is 0 0.4 I hat, and then 0 minus 0 0.3, which is going to be minus 0 0.3 j hat. So this is our vector. The magnitude, I believe the magnitude is going to be the same. 0 0.4 squared plus 0 0.3 squared, 0 0.5. The unit vector, that's gonna be 0 0.4 over 0 0.5 I hat minus 0 0.3 over 0 0.5 j hat. After finding the the unit vector, let's find the magnitude of our force. Our force, which is 1 on 3, will be K Q1 Q3 over R squared of 1 and 3, and their unit vector, which is going to be 9 by 10 to the 9 multiplied by 2 by 10 to the negative 6, which is 2 microcoulombs, by 4 microcoulombs, all over 0 0.5 squared, which is our magnitude, multiplied by our unit vector 0 0.4 over 0 0.5 I hat minus 0 0.3 over 0 0.5 j hat. In fact, we can make something like a bracket here to show that we are going to multiply this one by one. So this is going to be F1 on 3.
So you are going to get the same answers, but the difference is going to be the negative sign.
Yes, so what are the answers? That was 0 point something here. 0 point what?
0.23.
0.23. I had minus 0. 0.17 J had newtons. Now let's find what the net force. So F net is equal to 0.4. In fact, before I write the values, that's going to be F1 on 3 plus F2 on 3. So that's going to be 0.4 I hat minus 0.3 J hat plus 0.4 I hat plus 0.3 J hat. These two cancel. We have 0.8. Sorry guys, I have never done such a mistake. Yeah, first semester, second semester. So the value here was 0.223. Yeah. Someone almost collapsed. Like, what was going on? You. Alright, cancel. 0.46. I had newtons. Yeah, it was a long one. So guys, why were you lost? If you were lost, raise your hand if you want us to move on and you were not lost. Why were you lost? Please raise your voice.
I was not lost, say.
Oh, okay. You were not lost. Lindo? Lindo, are you here? You guys. Lindo is not here.
I'm here, sir.
Oh, why were you lost?
In the second part, sir.
The second part. Which one is the second part?
Where we were finding the unit vector.
Oh, the unit vector. Let's see. Which is this part, right?
Yes.
Okay, so we went on our diagram and we said we want to find this distance. But this distance is only going to help us with the magnitude of the distance between these two charges. If we are going to add two forces, or if we are going to define force as magnitude and direction, we are going to need the magnitude, which is just this part. And the unit vector gives us the direction. So that's why you need to find the unit vector. In order to find the unit vector, you need to first find the vector itself, which is the vector from Q2 to Q3. Now, because this is displacement, to find the vector from Q2 to Q3, we are going to treat this as one point, and this point has the coordinates 0 in the x, negative 0.3 in the y. This is our first point. We call it P1. And on this part, on Q3, we will call it point 2. And it is on 0.4 on the x and 0 on the y. It's not moving up or down on the y. Now to find r as a vector, we first need to find it as a vector. We are going to say it is equal to subtracting these 2 points, which is the ending point minus the first point. So right now, P1 and P2 are called position vectors. If the coordinates of a point are used as a vector, you call them position vectors. Now, because they tell you the position of that vector, so of that quantity. Now, point 2 is 0.4, comma 0. When you subtract these two, you subtract x with x, y with y. So we said 0.4 minus 0, and we got 0.4. The direction is in the x, so we use I hat. And then in the y, we are going to say 0 minus negative 0.3. 0 minus negative 0.3, which gives us a positive value of 0.3 in the j hat. Now, after finding this as a vector, to find the magnitude, we are going to say the unit vector, to find, yes, the magnitude, sorry, not the unit vector. To find the magnitude, we use Pythagorean theorem, which says take the magnitudes, square them, and take the square root. Take the components, square them, and take the square root. And we found it to be 0.5. And now that we have the magnitude, we take the unit vector, which says the unit vector is the vector over its magnitude. The vector is 0.4, the magnitude is 0.5 plus 0.3 over 0.5. So this is our unit vector.
Okay, so I get it.
It's clear. All right. So we are done with this question. In the absence of any more questions, we can move on, right? So we have 15 minutes. I'm not sure on where it's gonna put us, but we will see. So we were talking about Coulomb's law, and we said Coulomb's law gives us the electric force, which is the force that these charged objects exert on each other. Now, or on other objects, because if they are now more than one, it is other objects. So from it we can define, from Coulomb's law we can define electric field, which is that force over a single charge, over one charge. Now we want to know how much this force is on 1 coulomb. On 1 coulomb of charge, how much is this force? So that's where we find the electric field. We just divide by the charge we call the test charge. So in this diagram, you have this charge that you could say is the source of the electric field. It is the charge that is going to give us the electric force, and Q0 is the test charge. It is the charge that we are going to test how much electric field is due to this big charge. This is what we test with This is the source. Now, if the source and the charge have the same direction, the same charge, the electric field and the force are in the same direction. This is to say, if the electric field, okay, before I move on, the electric field is usually from positive to negative. So, if, it is from positive to negative. So, if now your charge is a positive charge, the force is in the same direction as the electric field. This is what also says here. We will look into it more. But now, if the sign of the electric field and the charge are not the same, the force is in the opposite direction, you will see what we mean. Maybe before we move on, I can show you some small Anyana diagram. So you will have positive on this side and then negative on this side. If your charge is positive, it is repelled. It moves from positive to negative. It is repelled. So this is the electric field. The electric field from positive to negative. But if your charge is negative, it is pulled in this direction. The electric field is still from positive to negative, but the charge is pulled in the opposite direction to the electric field. Therefore, the force is negative due to the electric field. Right now, the force we are going to define is no longer due to one charge, but it is now due to the electric field. This one charge creates an electric field around it. It creates an electric field. So that's what is going to happen in the next slides. So this is the source, this is the test. So this is how you are going to define your unit vector. The unit vector is from the source to the charge, to the test charge. So as we have just said, if now in this case our source is positive, so it creates the electric field which is away from the test charge. If the electric field is positive, its effect on the test charge is the field which is moving away from the test charge. It is moving away from it. If it was that force, remember, if we were referring to the force Q1, Q2 over R squared, remember the force of the positive charge on this one would be repelling it away. Do you see that? It would repel it away. But if now the source of the electric field is negative, it pulls it towards it. It pulls it towards it. So now the electric field is into the source. Here it was away from the source. Here it is into the source. I hope you see this difference. If it wasn't of time, we will continue. But unfortunately, I have to be in another meeting right now at 8. So I can't finish up these 8 minutes that is left. So we will finish up our session when we meet again. I will confirm in the group when is our next session. I will confirm in time. Are there any questions, suggestions? Hello? If there is none, see you when you see me. I'll see you when I see you. Have a good day. Have your first good day of the first semester. Second semester.